Well, hello again. In this example, you will learn how to solve for internal moments in a multi-span beam using the moment distribution method. But specifically, we will balance one joint at a time. We're going to be taking a look at this 3-span continuous beam. Once again, noting that we're being asked to balance one joint at a time. First thing we need to do is identify the joints. And once we've identified those, we need to go ahead and lock those against rotation. Once we have locked them against rotation, we recognize that we have 3 members now that are fixed at each end. So this allows us to begin computing our stiffness factors for the individual members. I'm going to focus on joint B right now. So the stiffness at joint B due to member BA is 4EI over the length, which is 30. Stiffness at joint B due to member BC is 4EI over 20. Stiffness for CB, so that's joint C, 4EI over the length of member CB, 20. Stiffness at joint CD, 4EI over 30. And recognizing in all of this that the moment of inertia is constant for the entire length of the beam. Also implied in there is that the material modulus of elasticity is the same across the entire length of the beam as well. So we can now compute our distribution factors. We're going to look at joint B first. Distribution factor of BA is equal to the stiffness of BA over the total stiffness at that joint. So that's just the summation of everything that's coming in at that joint. So that'll work out to be 0.4. Distribution factor BC, so the other member coming into that joint, can easily be found through this computation, which is 0.6. The reason being, we know that all distribution factors at a particular joint must sum up to be equal to 1.0. No other option there. Let's look at joint C. So we will take the stiffness for member CB and divide it by the total stiffness for the joint. And that will be equal to 0.6. dF of CD is equal to 1.0 minus 0.6 equals to 0.4. Please recognize what you're going to see here is you are going to see that E value and the I value have been conveniently dropped off of these. The reason being is because they are constant across the entire length of the beam, and so they end up canceling out. But if they were not constant, you would have to explicitly enter them into the equations right here. Next order of business will be to compute the fixed end moments due to the various loading scenarios on each beam. The way we will get that is by looking at beam charts. We've got fixed beam with a uniform load and a fixed beam with a point load in the middle. And so the computations that would be happening here would be 4 kips per foot times 20 feet squared over 12, or we do have a beam that is 30 feet long, so we will get 30 feet squared over 12. Down here we have 30 kips, 30 feet, all divided by 8 is what would be happening. You do the calculations on that. You can very easily get what the reactions are back here. This would be 112.5 kip feet, 112.5. This one works out to be 300, 133.3. All of those having units of kips and feet. And what we want to do is remember that in the moment distribution method, we are assuming that when a moment is clockwise, it is positive. When it's counterclockwise, it's negative. And that's the way it's going to show up when we assemble our table. For example here, since that's counterclockwise, it'll be a negative. That'll be a positive. Let's go ahead and assemble our table then. I'm going to label the joints A, B, C, and D. And then I'm going to list the distribution factors that I have computed for this. So distribution factor for member BA, we decided was 0.4, but for BC it was 0.6. And then for CB it was 0.6, for CD 0.4. And then we need the distribution factors for point A and point D. I want you to notice here that prior to locking this, that was a roller support, which means it had a 0 moment there. It's also the only member coming in to that location, which means if I apply a moment at joint A, the entire moment has to be taken by member AB. That will require then that the distribution factor of AB is equal to 1.0. It takes all of the moment. In a like fashion, the distribution factor at joint D for DC is 1.0. We can get the fixed end moments translated over here. So this will be negative 112.5, positive 112.5, negative 133.3, positive 133.3, negative 300, and a positive 300. So we are going to start balancing the joints one at a time. Remember that a joint is going to be balanced when the moments at that joint sum up to be equal to 0. So I'm going to just go through this methodically, and I'm going to start with the one that is the farthest out, and that is that the moment at joint B shows up to be 300, which means it doesn't sum up to be 0, and thus I need to go ahead and I need to add a negative 300 to that joint and distribute it according to this distribution factor, which means what? It means that it takes all of that load. And then I'm going to let there be a carryover. Since all the members are fixed, there's a carryover 1/2. That carryover will come over here at being 150. Once I've handled that, I'm going to go ahead and draw a line indicating that I have completed the distribution of one of those joints. Now I'm just going to work across the joints. The next thing I'm going to do is I'm going to handle the distribution of joint C. Now to make sure that we understand what's going on, I want to show you the explicit calculations that I'm going to use for joint C. I'll write the numbers down and then we'll go back to the table and make sure we understand where those came from. 133.3 minus 300 minus 150 is equal to negative 316.7. That tells me how far out of balance joint C is, which means I would need to add a 316.7 moment to that particular joint in order for it to work out. So I would take that and I would distribute it according to the distribution factors. So I'd get negative 0.6 times the negative 316.7. That'll give me 190.02. Then let's see how much goes on the other side of the joint. That'll give me 126.68. So let's go back here. I'm going to write that in. We get 190.02, 126.68. So where did those numbers come from? I want you to notice there's 3 numbers. And what I did is I took all the numbers that were above that dividing line right there. I added them up. That would tell me how much moment is being applied to that joint. Then I can go ahead and do the distributions as they proceed. Now I need to do a carryover of 1/2 to each of the individual sides. So this will come out to be 63.34. This will come out to be 95.01. I'm going to draw a horizontal line indicating that I've now balanced that particular joint. As I move on to the next one, joint B, I will take these three numbers. In fact, let's go ahead and do that calculation. Joint B here will give us 112.5 minus 133.3 plus 95.01 is equal to 74.01. I'll go ahead and distribute that. That'll give me negative 29.68 and negative 44.53, which I can now put back into this table. So we'll handle the distribution for joint B, negative 29.68, negative 44.53. We then need to handle the carryovers, which would be 1/2 of that, so negative 14.84, and this one will be negative 22.26. Let me go ahead and draw a horizontal line, indicating that we've handled that one. And then we are prepared to balance the next joint. That is this one. So what I've got to do is I've got to take the sum total of that, distribute it according to this, which means that my next distribution, I would add 127.34, draw the line. That will carry over here at 63.67. So here's where you have to be careful, because we're going to go back to joint D and just work our way across again. What you want to do to figure out what you've got going on is you would then take everything that is below the line that I drew. So here was the line that I drew, 63.34, and I distribute that accordingly. So watch this. I will take negative 63.34. Of course, there's going to be a carryover here of negative 31.67. And then I am ready to move on to the next joint. I'll draw a line here so that I don't get confused on that. Then as I go to balance the next joint, joint C, I will consider everything that is below the line that I drew last time I balanced joint C. So that would be these numbers. And I would then distribute those accordingly. So that one would work out to be 32.36 and 21.57. I would draw the line, do a carryover, 10.79, do a carryover here of 16.18. Then I'm ready to do the next joint, and I would look at everything that happened since the last time I balanced joint B. I could distribute that accordingly. That would work out to be negative 31.94, negative 47.91. You'd carry those over, so on and so forth. What I have done is I have provided for you a complete table that shows you which joint I'm balancing and also the carryover that has happened. So you can follow that all the way through, and by the time you get to the point where your carryovers become very small, which is what we've got going on here. By the way, let's be very clear. Here's a carryover. Here's a carryover. Carryover. Carryover, and so forth, all the way down. By the time your carryovers get to be very small, you can eventually stop that. And then what you want to do is just go ahead and sum up everything that is occurring in each of the columns. And if you've done it right, each of these should come out to be very close to zero. They're not going to be exact, simply because we haven't done enough iterations, but they are close enough. I want to give you what the numbers would be if an exact analysis had been. It would be 115.89, 326.82, and this one should be 0. So that would be the exact numbers you would get. And as you recognize this, we've gotten very, very close, which is sufficient for us. That concludes this example. As always, it's a beautiful day for studying structures.